Welcome to the today's webinar series arranged by IEEE Young Professionals Bangladesh and IEEE Bangladesh section, Meet the Young Professionals. Today we have Dr. Mohammad Selim Habib with us to deliver his talk on recent advances in hollow fibers, technology and applications. Let me introduce himself first. Dr. Mohammad Selim Habib received his BSc and MSc degrees in Electrical and Electronic Engineering from Russian University of Engineering and Technology, Rajshahi, Bangladesh in 2008 and 2012 respectively. He received a PhD degree in Photonic Engineering from the Technical University of Denmark, ETU, in 2017. After finishing the PhD, he joined as a postdoctoral researcher in fiber sensors and supercontinuum group at the Department of Photonics Engineering, DTU. After completing his postdoctoral fellowship at DTU, he worked as a postdoctoral research associate at SRIO, the College of Optics and Photonics, University of Central Florida, the USA, from September 2017 to August 2019. Now, he is an assistant professor of electrical and computer engineering at Florida Polytechnic University, USA. His research mainly focuses on design, fabrication, and characterization of low-loss hollow core fiber in the near IR to mid-IR, light-gas nonlinear interaction in hollow core fibers, supercontinuum generation, and multimode nonlinear optics. He has published more than 40 articles in referred journals. Dr. Habib is a senior member of the Institute of Electrical and Electronics Engineers, IEEE, Optical Society of America, Early Careers member, and Executive Officer of OSA Fiber Modeling and Fabrication Group. Dr. Habib is an Associate Editor of IEEE Access and Featured Editor of Applied Optics, OSA. He received the University Gold Medal Award from Russian University of Engineering and Technology in 2024. So I would like to request Dr. Mohammad Selim Habib to start his talk among us. Sir, the floor is yours.
Thank you, Ajmain, for your introduction. So can you hear me all?
Yes, sir.
Yes, right.
Okay. You can hear me, right? It's clear?
Yeah, it's clear.
Okay, thank you very much. Thank you very much for your introduction and for the invitation for this talk on recent advances in hollow core fibers, technology and applications. So basically, I'll be talking on a very specific kind of fibers today, which I believe is very interesting, has potential applications in many applications from medical, fiber optics communication, and so on and so forth. So I will share my screen here. Okay, so I think, okay, so let's start. I can share my screen. Can you see my screen now?
No, sir, not yet.
Not yet, right. So I'm not sure that why I cannot share my screens. Let me check here. Okay.
I have already given you the access.
Okay, so yeah, I'm going there.
Yes, sir, we can see.
Okay, that's great. Okay, so I will try my best to cover these topics today. So first of all, I will start with some very basic introduction of optical fibers that you probably know, the conventional optical fibers nowadays, which has been normally using in optical fiber communication. Then I will go to more details on specific fibers, which is called hollow core fibers, which has lots of applications nowadays. I will talk about the design, modeling of these fibers, characterization, and also fabrication. And in the second part, which is I think is a bit high-level talk, is about nonlinear application of hollow core fibers. Basically, I will be talking about the light-gas interaction in fibers. How can we really compress the pulse? And it's called ultrashort pulse compression. Then I'll be talking about multi-octave supercontinuum generation, some noise and stability analysis of this supercontinuum generation, and deep UV light generation, if the time permits today. Okay, so I guess that most of you know the telecom fibers. I think it's one of the greatest inventions ever because this is pretty simple in nature. It's easy to fabricate. However, this fiber used in telecom industries for a couple of decades now, and can be transmit the data, a huge amount of data you can transmit over a very long span. And it's pretty thin. It's comparable to the human hair. It's just slightly probably thicker than the human hair. So this is a typical optical fiber that normally used nowadays in the telecom industries, which typically has a core. We call it a core, and this is typically 9 to 100 micrometer, depending on the applications, surrounded by cladding, which is typically standard 125 micron. Then we normally use a couple of protective layers so that we can protect the fiber. So when we bend the fiber so that the fiber doesn't break or any external perturbation, it remains very stable. So here are some very important figures of optical fibers, why this is very important to study specifically in fiber optics communication. Because you can draw a very long piece of fiber, for example, 50 kilometer. We call this a one spool of fiber, and the size is very, very tiny. Is 250 or 200 micrometer. It depends. And as you can see, the weight is like 1 kilometer of fiber is only 70 grams. It's very light in weight. And also nowadays, if you see the production is like larger than 400 million per kilometer has been produced. It means that this is 800 times than if you go from the Earth to Moon, the distance. And over the 35 years, there are lots of inventions, innovations, and patents has been filed. And it's, of course, it's a long-term reliable technique. And we call it a fix and forget system. And another question is what type of basically the materials we normally used for a fiber optics or any fiber optics communication or any other applications for fibers. So the left column shows the various glasses it can be used. So for example, if you use a lime soda bottle, so if you have a Coke bottle that we normally do, we drink, so it has a gigantic adsorption, so we cannot use it. Window glass, it also has a very, very high loss. It means that it will not transmit any light. And if you go to the optical fiber that we normally use, it's called fused silica F300. It has only 0.2 dB per kilometer at 1.5 micron. So the loss level shows here, this is at 1.5 microns. So if you compare here, it means that as it has a very low loss or attenuation, we can use a very long piece of fiber. For example, it's an equivalent figure. And as you see from the lime soda bottle to the optical fiber, is exponentially increases the length. So we can increase the length if we use a pure silica. Though it's expensive, but we can use it compared to the other glasses. So fiber types, basically there are two types of fiber. One is called solid core fiber, another is called hollow core fiber. So today I will mainly focus on hollow core fiber. And the solid core fiber can be divided into two types. One is called conventional optical fiber, and there is the photonic crystal fiber, which is more, recent, has plenty of applications though. And hollow core fiber we can categorize into two types based on the guiding mechanism, how the light will guide in the core. One type is called photonic bandgap, another is called anti-resonant fiber, which is pretty new. So it is the cross-sectional view of a conventional fiber. So it's pretty simple. It has a core and surrounded by cladding. Typically, core has a higher refractive index and cladding has a lower refractive index. But both materials here used silica. But normally we use the doping to increase the refractive index of the core. So we normally use the germanium doped silica. And for the cladding, we use silica, pure silica. So the core diameter is typically 8 to 10 micrometer. Cladding is 125. And the loss reported at 1550 nanometer, also called 1.55 micron, is extremely low. This is 0.15 dB per kilometer. And how the light will guide it in the core is pretty basic from the physics. It's total internal reflection because the core has a higher refractive index than the cladding. However, the main problem of this fiber is that it's very limited application. This kind of fiber normally used in telecom, not other applications. So this is the major disadvantages. And also the problem is here, you have a very low index contrast because the core and cladding has a very similar refractive index. So you cannot do so much for other applications. Whereas another solid core fiber has been immersed in the last decade. This is called photonic crystal fiber. It has a tiny ear holes along the length of the fiber. The major advantage it is like a single material fiber. So if you have a silica, you make some holes, you stack it in the fabrication process. However, it has a very high index contrast, wider design space. The main problem is the fabrication. It's challenging. The fabrication is challenging, and you cannot make very long piece of fiber like conventional optical fibers. So going to the hollow core fiber, actually it was first proposed by Philip Russell, who is now the director of Max Planck Institute. Is a very big researcher in the fiber optics industry. He first proposed in 1991 in a Clio conference in USA. Whether he proposed that what if the core is empty? Empty means that the core is now just air, and the cladding is the air and silica layers. And he first proposed in 1991, and nowadays it has been used a lot for many applications. For example, medical application, laser, and other applications too. However, the guiding mechanism is very complex, and the light normally guides. This is called a photonic bandgap effect. So what are the advantages of using this hollow core fiber technology? Is because light will be guided in air. What it means is that when the light guides in air, you can transmit enormous amount of data because the information will be traveled in the form of light. And the light, when the light will travel in the air, it means that it can travel at the velocity of light. So it's like an infinite bandwidth. Theoretically, you can transmit. And the lowest loss reported is 1.7 dB per kilometer, which is pretty high compared to conventional optical fiber. And it also has a low band loss. It means that if you bend the fiber, it's pretty flexible. It doesn't have band loss. However, the main problem here is that it has limited transmission window. It does not guide light over a huge transmission band. Also, it suffers from surface scattering loss. It means that when we fabricate a fiber in a draw tower, we saw in a microscopic image or scanning electron microscope that it has some roughness. And if you have some roughness at the shorter wavelength, the light can scatter from the surface, and it induces some extra loss from the fiber. And it also suffers from surface mode loss and limited power handling capacity. It means that you cannot just launch huge amount of power because it has some limited damage threshold. However, this is the other kind of fiber. This is also hollow core fiber, but this is much more exciting. Plenty of potential applications. It was first proposed in 2011 by a Russian group, Priamikov, which is one of my very good friend. He proposed this fiber in 2011 in a seminal paper in Optics Express. He proposed that what if the fiber is hollow core, however, there will be very tiny silica layers in the cladding. It's pretty simple, rather than the other structure that I shown earlier, where the core is air, and these tiny air holes, as you can see here, the air holes, this is made of silica. But these tiny silica layers can be from 300 nanometer to 1000 nanometer, or even bigger, depending on the applications, which wavelength you want to operate this fiber. But the guiding mechanism, as the light guide will be in the air, is pretty complex. And this is called inhibited coupling and anti-resonance effect, which was first proposed in 2002 in a science paper from Benabit group in France. They first proposed this fiber that it can be guided light in air. However, it's a new technique, a very novel technique, which is called inhibited coupling. It means that we call a fundamental mode, which is called LP01 mode. It doesn't couple with other core guided or cladding modes. They are completely separated, and that's why it gives a very high, large transmission window, as well as it has very low loss. So what are the advantages? Why we have to design this kind of fiber? Because it's a pretty simple structure compared to the other structures, hollow core fibers. It has an extremely low loss, 7.7 dB per kilometer, but not extremely yet, because you have to design another fiber for doing so. But still, for this simple structure in 2017 from Benabit group in France, they proposed that yes, we can make 7.7 dB per kilometer with a very simple structure. However, compared to the hollow core bandgap fibers, it has very low surface scattering loss, broad transmission window. It means that we can make this fiber, for example, transmit light 1 octave. We say 1 octave is an enormous bandwidth. Low light glass overlap. It means that almost 99.99% of the light will be guided in the core, which is air. However, only a tiny fraction of the light goes to the cladding, 0.1% or even less. It means you can launch enormous amount of energy with a high energy laser into the core. And the major advantage here is that as the light will be guided in the core, which is air, it means that it has a low latency, low time delay. So theoretically, you can have like infinite bandwidth. And it also has long light matter interaction. That means I'll be talking to this topic in my later slides. And also it supports like single mode operation. Even though the core diameter is pretty big, by carefully designing this fiber, you can make it single moded. So just one mode will propagate through the fiber. Here is the guiding mechanism. It's pretty complex. I'm not gonna go details, but I'm giving a very basic how to do it. So as I said earlier, that this fiber guides light based on the inhibited coupling and the anti-resonance effect. What it means is that so these silica layers actually acts as a fabrication resonator. So at some wavelength, it reflects and trapped into the core. And in doing so, actually, if you want to analyze this, you don't have to solve the full structure. You can take a very tiny unit cell. We say the unit cell, as you can see here at the top of the figure, we take it like a unit cell, and we solved like 500 modes. It's pretty complex. You need a very high configuration computer to do it. And also you need the appropriate boundary condition to solve it. So we normally solve like 500 modes. And as you can see here, that you can track which is the LP01 mode, which one is the LP11, 31, 02, and so on and so forth, and the cladding modes, and also the we call strut modes or silica modes. You can easily find it. So as you can see here, that the solid lines here, it shows that this is the air guided modes, but it's very complex. But in this way, you can figure it out what is the difference between the guiding mechanism of these novel hollow core fibers and the 14 bandgap fibers. So what are the challenges of this fiber? But it's still, you know, this 7.7 dB per kilometer is not promising, because the conventional optical fiber that we are using nowadays, it has a loss of 0.15 dB per kilometer, but it is 7.7 dB per kilometer. So the question is that, can we make a fiber which can give us less than 1 dB per kilometer? The answer is yes, but we have to modify the design. And the main problem is that, you know, sorry? Can you hear me?
Yes, sir, we can. Please continue.
I can just hear some sound, so that's why I stopped. Okay, thanks. So another problem is that when you bend the fiber, the light can leak easily to the cladding. So this is the major problem using these fibers. So how to, you know, make an improvement so that the loss will be low, as well as the bend loss when you bend the fiber will also have a very low loss. It was first proposed in 2014 when I just started my PhD in Denmark. It's one of the world leading group in University of Bath in UK. Probably you know the name Jonathan Knight, Tim Burks, and Philip Russell. They are the pioneer for hollow core fibers technology. From their group, actually, University of Bath, they first proposed that what if we include another tiny tubes inside the original tubes? And it turns out that that when we insert this kind of tubes, that it significantly reduces the loss. The reason is that it sufficiently increases the inhibited coupling. It means that the core guided mode and the cladding, they don't talk each other, so that it gives you very, very low loss, the propagation loss and also the band loss. So here is the few fiber that has been that have been fabricated during the last 20 years. The first row is 14 bandgap fiber, and the second row is the hollow core anti-resonant fiber. There, I mean, if you see that as the time progresses from 2000 or 1991 to 2019, the researchers have made a very good progress of these fibers. So I can show here, so the recent hollow core fiber designs from different research groups, including our research group in Creole, University of Bath, University of Southampton, also in UK, in France. The different researchers really worked hard to make a good fibers. Yes, another question is that whether we can make the fiber single moded that I earlier. The answer is yes, we can do it. So I did some modeling a couple of months ago, and this work is under revision in GL3, Journal of Light of Technology. So as you can see here, the LP01 mode, we say this is the fundamental mode. It's very well guided in the core, while there is the other modes, LP11, we call it the second order mode, LP21, and the cladding mode. They are really leaky. That means if we properly design the fiber, we can make it single moded. And this is very interesting that how can we achieve? This is the question. The answer is that if we change the diameter of the nested tubes or the smaller tubes, we can make it. As you can see here, when we change the diameter of the small tubes, the left figure, it shows that the loss, the second row, it shows that the LP01 mode doesn't change. I mean, the loss remains almost constant, whether the other modes is really leaky. The reason is that so that in order to get better intuition and understanding what's going on, that's why we have to plot also the dispersion curve, which is shown at the top of the figure. As you can see here, that the refractive index of the LP01 mode remains constant. It doesn't change. Whereas the LP11, LP21, 02, and 31, they remain also constant or fixed. However, at some point, they have a coupling between the core and cladding. You can see, and when it occurs, it means that that particular mode will experience high loss because there is a strong coupling between the core mode and the cladding mode. So in this way, we can make this fiber single moded. It's pretty simple. Now the question is whether we can beat the loss of conventional optical fiber using this novel hollow core fiber technology. The answer is yes. So we did some simulation earlier this year, and it turns out that we can even make it 0.1 dB per kilometer. And how can we achieve? So I think I was the first ever proposed this structure, the 5 tubes, because if you see in the literature, most of the researchers come up with either 6 tube, that means in the clearing either 6 tube, 7 tube, 8 tube, 9 tube, or 10 tube. So actually in the one of the Russian guys, and later I first proposed and I really thoroughly investigated that yes, this 5 tube has even better optical properties than the 6, 7, or 8 tubes. What we did here, we slightly actually change the dimension of the nested tubes. We make it slightly elliptical. One might ask, how can we make it? And it's pretty obvious that when you make a fiber like this in the door tower, it's natural that it will come up with an ellipse shape. You cannot, I mean, it's very difficult. It's kind of impossible to make it perfect circular. It's a drawing process. You can make it. So this is good in one sense that if you make a ellipse shape, that it gives a better performance. So here is the figure, a loss figure, and it shows that if we change the ellipticity, that means if we change the dimension of one of the axes of the nested tubes, we can make 0.1 dB per kilometer at 1550 nanometer. So in this way, we can actually beat the loss of conventional optical fiber, and we can replace this fiber probably in short reach data communication. So in my second part, I'll be talking about modeling of hollow core fiber. This is very important because the modeling of hollow core fiber is very demanding and it's challenging. It's complex. It's not solid core fiber. So we normally use finite element method solver, which is more accurate than finite difference, of course. And we use COMSOL multiphysics because it's one of the state of the art software in the market. However, the mesh size and the perfectly meshed layer boundary conditions has to be well optimized, and that's the problem. So you have to be very careful when you design these hollow core fibers. So now the question is that when we design the fiber, how accurate it is in AFM solver, which is COMSOL multiphysics, how authentic it is. So here is the curve. So I did the simulation back to, I think, 2018, 2 years back from now. As you can see here that this, it's in the left way shows the scanning electron microscope image. And the fiber was fabricated in ORC, Optoelectronics Research Center in University of Southampton, UK. So now they are the world leading group in hollow core fiber industry. The fiber has a core diameter of 31 micron. Silica wall thickness was 1170 nanometer. So what I did and what we do normally, in order to get accurate result, we extract this ACM image to COMSOL server. It's a difficult job, but you have to do it to get the accurate information, accurate result of this fiber for accurately doing the optical properties of this fiber. So as you can see, it's very well agreement between the simulation and experiment. But you have to also think about here is that when we design and model this fiber, there are plenty of losses involved. It's not only the confinement loss, it has also microband loss, it has surface scattering loss, it has attenuation from the silica layer. So lots of loss can add to get the total propagation loss. So I think it's a tremendous that we did, that the simulation and the experiment, they really will meshed together. Now going to the conventional optical fiber, hollow core fiber. So the black line is the conventional fiber, is a measured loss, and it gives 0.15 dB per kilometer at 1550 nanometer. Photonic bandgap fiber, it normally gives 1.7 dB per kilometer, the lowest reported loss. But the problem is, you can see here that it has a limited transmission window. So we cannot use so many applications for this fiber. And the single nested tubes, we can make less than 1 dB per kilometer. So if we add another layer, so we can actually beat the conventional optical fiber in this way. But it's very challenging and difficult to make these double nested hollow core interlacing fibers. Well, so this figure shows the hollow core fiber evaluations over the years. As I said earlier, that this generation, the first generation of anti-resonant fiber, was first proposed in 2002, and it's a seminal paper in Science, published by a French group. The group leader is Feta Benabit. They first proposed this, and they published in Science. But the loss was not good. It's enormous, 3000 dB per kilometer. But the idea was to use for nonlinear applications, not for fibers. Then in 2011, from the same group, no, I think it's from the UK, Ying Wang, she developed this fiber. It's called hypocycloid type fiber. It's 150 dB per kilometer. In 2013, is a Russian group. They came up with 50 dB per kilometer. And in 2017, from Benabit group, they published a paper in Optica, and they came up with 7.7 dB per kilometer. So as you can see that in over the years, from different research group, they propose different structure to reduce the loss, and it's a loss of effort actually. However, so these fibers that I'm showing now is a record low loss now, and it is all of the fibers have been fabricated in University of Southampton in UK. So they came up with nested tube, and they fabricated 1.3 dB per kilometer in 2018. But as you can see, the loss in 2019 and 2020 from 1.3 dB per kilometer to 0.28. So we are very close to the conventional optical fiber. But theoretically, we can even make less. But they're really trying and focusing on these fibers so that they can really beat conventional optical fibers. However, one thing I want to actually mention here, this is very important, is that the shape of the structure is very important. Even the slight change of the structure, it can give you very high loss, and if there is any irregularities during the fabrication, it can give you very high loss. So fiber fabrication and characterization. So this is actually my previous group that I used to work in Creole. It's one of the top 3 groups in the United States. So I was so lucky enough to work there for 2 years. So we actually fabricate so many fibers, not only hollow core fibers, we did so many fibers, for example, for high power fiber lasers, fiber optics communication, and so on and so forth. So the left one shows the clean loop that we make the materials for the fibers. The second one, so I was actually doing the characterization of fiber. So this is the ACM image. And the third one is the fiber dot hour. Yes. And this is called fiber preform stacking. As I remember, I did it in 2016 when I was a visiting research scholar in Creole back to 2016. So for the fiber preform stacking, you have to do it manually. So there is no machine to do it. You have to do it manually, and it's really time consuming. It can take a couple of days to make this preform, and you have to be very accurate, to get low loss fiber designs. Here is the fiber fabrication. I want to show you how we draw the fiber. So this is the fiber draw tower that we have in Creole. I can play the video. Yes. So at the top we have the furnace, and the fiber is coming here. So this portion we call coating. So we coat the fiber, then we draw the fiber, and the next step is to spool the fiber in a drum. Okay. And we have to also always monitor the fiber. We always need to monitor the fiber so that it doesn't break. So he is the head of fabrication in Creole. Okay. So this is the end of my first part, which I tried to talk about hollow core fiber design and fabrication. Now I will go to the more application. However, this will be a bit high level talk, I believe, because it involves nonlinear applications of fiber. Yes. So what we do for the nonlinear applications, and in order to do the nonlinear application, what we do, we actually fill the fiber with some noble gases. For example, helium, neon, argon, krypton. These noble gases, we fill the fiber with gases. What happens is that when the fiber is empty, there is no inside. It has we call the anomalous dispersion. That means it has a negative dispersion. And when we fill with gas, so the anomalous dispersion can be counterbalanced, and it can give you normal dispersion, the total dispersion. As you can see here, one of the main advantages of using this system is that by simply changing the pressure of the gas, you can change the dispersion. So in this figure, I change from 0 to 30 bar, and as you can see, the dispersion can be changed a lot. Also, the zero dispersion can be changed, and it has a negative dispersion, which can be used for soliton and many other applications. You can form a soliton, you can make a superconducting generation from it. And the good thing of this particular type of fiber, rather than the hollow core bandgap fiber, is that it guides very broadband window. It is a low light glass overlap, low and anomalous dispersion. And also you can change the pressure of the gas. So if you go to the lab, you just change the pressure of the gas so that you can change the dispersion. And the second advantage of using this system is that not only the dispersion, by changing the pressure of the gas, you can simply change the zero dispersion wavelength and also the nonlinearity, which is very important. So we have to have a high nonlinearity in order to get supercontinuous generation. And another important advantage is that this gas nonlinearity normally scales linearly with gas density or with gas pressure. Yes. So in order to do it, we normally solve a very complex system, which is called, this is called unidirectional pulse propagation equation. So we normally solve in frequency domain rather than the time domain, which is more efficient. Where E is the electric field, beta is the propagation constant, Vg is the velocity of the light, or the pulse propagating. Sorry, this is the pulse propagation. Alpha is the attenuation coefficient. C is the velocity of light, and PNL is the nonlinear polarization. Basically, it involves the Kerr nonlinearity. If you are familiar with this, you probably know what it is. It's the Kerr nonlinearity. Okay, so what we do, first of all, we can generate UV light source, because there is no system that you can really efficiently generate UV light or deep UV light with the semiconductor laser or other crystals. It's very difficult. You cannot get it. So one of the way to do it, you fill the fiber with gas. So for example, in this fiber, we have a 30 micrometer core diameter. We fill with argon gas 5 bar pressure, which is very high pressure, and we have to be very, we normally careful when we put such amount of pressure because it's very dangerous as well. And we launch 1 microjoule of energy at 800 nanometer, 30 femtosecond of pulse. As you can see, the right one shows the temporal profile. Initially, the pulse was 30 femtosecond, and when it propagates to the fiber, it's compressing, and the pulse is becoming more pickier, more energetic, and we say at the maximum Sultan compression. For example, at 12 centimeter, it is enormous, and at this temporal compression stage, we call dispersive wave generation, and in this way, you can generate light at 300 nanometer of light, and also you can get a huge broadband supercontinuum source out of the fiber. Not only this, you can tune the dispersive wave by simply changing the pressure of the gas. So for example, you want to generate 500 nanometer, don't worry about it. You don't have to change anything. You just change the pressure of the gas. This is more exciting. So the main problem is that when the pulse gets compressed, it's really high peak intensity. It can be up to gigawatt. It's enormous. So what happens as we are using the gas, so the gas particles or molecule gas can get ionized and form plasma. So one effect of the nonlinear effect is the nonlinearity. The second effect is the ionization. So you can ionize the gas. It's pretty complex, very complex system. It might take a couple of days to run the simulation. If we have like this system and also other system, if we include all of the system, it might take a couple of days to solve it. Okay, so here is the experiment we do. We have a collaboration with Creole and also Technical University of Denmark, because the laser that we are using is very expensive. It's a couple of $1 million. So in Europe, there are just a couple of lasers of this kind that we have. We are really lucky to have this laser. As you can see here, that the experiment I did in back to 2000, I believe 2017 at DTU. The simulation of the experiment that you see that the dispersion measurement is well agreement with the simulation, as well as the loss. As you can see, the right figure, it shows the loss. They are very well agreement, the experiment and the simulation. So this is the experimental setup. As you can see that we normally use a TiSci laser, then we use the OPA. This is called optical parametric amplifier, so that we can tune the wavelength of the laser, and also we can amplify the laser. And then we are using some lenses, some gas cells, so that we can insert the fiber inside the gas cells. And at the processing unit, we normally use 2 cameras. One is called CCD-based spectrometer, and another is called IR spectrometer. As you can see at the bottom of the figure, it shows the gas cells, and the fiber is shown here. So it's pretty tricky to insert the fiber inside a gas cell. Okay, so in the recent years, we actually published some Nature scientific reports. We published 2 papers back to back, because we are the first group ever that we launch in the mid-infrared. It's 2.46 micrometer, and we got a very gigantic, gigantic 4.3 octave supercontinuum generation. So we are the first ever group that we this kind of supercontinuum from this gas-based application, nonlinear applications. And we also got a record 28% efficiency of the dispersive wave. And as you can see that this figure shows a comparison between the simulation and experiment. It's pretty identical, and it's also very well agreement with our experimental results. Yes, and so just recently we published this paper in scientific reports this year. And what we did, normally what happens when we use this kind of lasers, these lasers are not stable. it fluctuates. Even though it fluctuates, the light that comes out from the laser is pretty stable. So as you can see that we monitor over the like 120 hours, it means almost 5 days we monitor. And as you can see, the effort that we are getting from the fiber, it's pretty stable. It's pretty, so it doesn't change a lot. It's like 3% variation. It's pretty stable superconducting source that we can get out of our system. Going to the more complex system, so we say it's a tapering fiber. We can taper the fiber along the length, and what it does actually, it does that we can generate, for example, 100 nanometer of light. It's pretty novel idea, and I mean it's hard to get 100 nanometer light, but it has plenty of applications. For example, Navy, Air Force, they have lots of applications for this 100 nanometer. Also the X-ray. Yes, for the ultra-short pulse compression. So this experiment was done in collaboration with Creole and IANA in Germany. What it does, they pump 110 femtosecond in the mid-infrared at 2 micron, and they compress down to single cycle, which is a sub-cycle actually, 19.6 femtosecond from this system, and it's enormous. So you can get average power of 43 watt, which is a peak power of 1.4 gigawatt. So you can get a very high power from the system. So these are the list of the most significant work that we did over the years in Creole with collaboration with Cornell University, and also with DTU Photonic. I was involved with mostly simulation work, designing fibers, doing simulation with the nonlinear applications of fibers. So what we did, we basically, this is actually a summary of my talk today. We did actually design, characterization, and fabrication of low loss fibers. Still we are doing so that we can get really record low loss. We did light gas interaction in fibers. We can generate very high peak power, extremely short pulse from the system. We also analyzed stability and noise analysis from our system. So what are the applications that from this fiber that we can get it? So it can be used for high-speed data communication, because light normally travels in air, so that you can travel your information in the speed of light, because air has a refractive index of 1. So the phase velocity will be close to 1. The phase velocity will be close to the velocity of light. You can generate a deep UV mid-IR superconducting generation. So one of the applications is that to generate this mid-infrared is that, so you can detect early cancer detection, which is very useful. You can get it from the system. So you can have also higher power beam delivery, because it doesn't care, because the light will be gathered in the air. So there is no light that you can get in silica layers. So you can launch enormous amount of power. It means, what does it mean is that it can be used for laser machining, laser drilling. So if you have a robot in the robotic arm, if you have this kind of laser, so you launch a light with a very high power, and the laser doesn't break or burn because it doesn't see light in the silica layers. You can have a very ultra short pulse compression. It means that you can get a very gigantic superconducting source, which has plenty of applications. And also you can have mid-infrared lasers. So you can generate light at 4 micron, 5 micron, depending on which applications you want to use. So at the end of the talk, I would like to thank my collaborators, Professor Rodrigo, which was actually my postdoc supervisor. He was the principal investigator at Creole. And he was actually involved with hollow core fiber technology since its invention. So yeah, he knows a lot about hollow core fiber technology. I'm also very thankful with Jose Enrique, because he's the main fiber fabrication person in Creole. Also my PhD supervisor, Ole Bang, also Christos Marcos, one of my friends there. And also I'm thankful with Jeffrey Moses, Cornell University. We have a collaboration with him. So we are doing to generate the light at in the mid-infrared. And I'm so thankful for providing me the support from Air Force, Navy, and the National Science Foundation for my different grants. Thank you very much for your attention. I hope you enjoyed. And if you have any questions, feel free to ask me, or you can reach me out in my email. Thank you very much for your time. Thanks.
Thank you, sir, for your nice presentation. So I would like to invite the participants to ask any questions if you have. You can unmute yourself and ask the question directly to our speaker.
Assalamu
Waalaikumsalam.
Dr. Salim, this has been a very, very interesting presentation. Thank you very much.
Thank you very much. You too.
Doctor, I had one question for you. That is, you have been working with mid-infrared fibers, right?
Yes,
could you
right.
please suggest a few lasers that has high research potential in the mid-infrared range?
Okay, the problem is here that you cannot get like a mid-infrared laser like this, but it depends which wavelength you are talking about. I mean, which particular wavelength?
Sir, currently, mid-infrared, like the ones you're working at, it is, I think, it's above 4 micron, right? But for communication,
no. Actually, no. Actually, the laser that we launch, actually, it's 2.4, but we can go up to 4. The main problem is that when we scale down from 2 to 4 micrometer, the energy really drops.
Exactly.
It's the main problem. Okay, so what we do actually, we basically use a conventional laser like a Taisefai laser system, then we use the OPA system so that we can tune the laser and also we can get a very high peak power, because the system that we are using here, it requires enormous amount of energy. Otherwise, you cannot get any nonlinear effect. Okay, so you can use a Taisefai laser, but you have to use a very expensive, because these lasers are $1 million. Couple of $1 million, very expensive laser. So in the whole Europe, you have a couple of lasers. So we are very lucky that we have it in our lab.
So these are the lasers that you're using for testing the fibers?
No, we are doing some real life experiment, because
exactly,
we are doing this experiment because for early cancer detection. So it's
only cancer
tremendous.
detection. I see. Okay.
Not only cancer detection, you can get this laser for plenty of applications. For example, you know that the main applications of the mid-infrared is that the molecules, this is we call the fingerprint region. That means you can detect the various molecules. Okay, it's one of the, basically our main focus is the early cancer detection for sure, but also if you have laser like this, you can do that. Let's say you want to measure a loss from other fibers and you don't have this system, so you can use this laser to measure the transmission spectrum of other mid-infrared lasers. So this is another application of these lasers. But our main focus is the imaging technique. For example, early cancer detection. This is our main actually focusing now.
Sir, if I know in Waterloo University, there is someone called Professor Ramahi. So he has been working with microwave antennas to also carry out early detection of cancer in the first stage, actually. So have you guys, I don't know, like if you guys, I think so he completed most probably, because he gave a seminar in our university around last year. So far, I think so he has published the papers yet. So have you guys compared results or anything? Or, early stage of cancer detection has, let's say, for each person, they're actually different, right?
Yes, you're right. Each person has different technique. Yeah.
Exactly. So no, what I'm saying is, like, let's say for early detection, like the cancer cells in each person is actually different. It's never the same. So is your method similar to, now what I'm trying to ask is exactly that, your method can detect any type of cancer cells, or is it specific to someone?
Very good question. So actually, you know that this kind of research is very broad. So what we do actually, so I'm in the modeling and the experiment part of generating this laser source, right? So there is another group in our group. I mean, there's another group inside our group. They actually focused on the early cancer detection, not ours, because it requires imaging technique, it requires OCT system, and lots of things involved there. We normally don't do this. We normally do what we do. They say that, yes, we need a light source, let's say at 4 micrometer. So you have to generate very high energetic light source from there. Okay.
Yes, understood, sir.
Myself, I don't do it the like early cancer detection.
Okay, okay.
What
So,
we
sir, doctor,
generate
you have
light.
been working with simulations to generate the light
Not only
sources.
simulation, not only simulation, I also do the experiment, both.
So you also do the experiments. I see, very nice.
Yes.
So,
Yes.
doctor, sir, this research, you're doing it in your current university, or you did it back in DTU?
That's a very good question. Actually, I would say 50% of the work that I did in during my PhD,
Yes, sir.
and 50% work that I have done, in Creole in UCF.
Okay, okay. Thank you very much. And doctor, could you please, let's say, if you have any idea about what about the future potential of quantum cascade lasers?
Oh, it's a huge.
It's huge.
It's a huge, yes, but it's a very complex system. It's very complex. When you involved in quantum, it's really complex. Yeah.
No, I'm not involved. I'm currently working with quantum dash lasers and semiconductor lasers. So the power that I work with is very low, approximately 2 to 3 milliwatts or 4 to 5 milliwatts. So yes.
Not only this, there is another actually topic that I didn't get time to show you. We are also using the gas lasers, but the same system. So we pump at 1.5 micrometer with a very low amount of power, but we can also generate either 4 micrometer laser or a 5 micrometer, and this is called Raman scattering. So we fill with hydrogen gas, not the noble gases, because you know that the hydrogen has rotational and vibrational Raman. So if we pump with 1.5 or 1.6, depending on the transition level, you can generate either at 4, 4.5, or even you can go up to 10 micrometer.
Thank you, doctor. Thank you very much. Okay. Doctor, could we please have your email ID so we can contact you?
I think my email address should be in the front of the slide, but I can, share with you. Yeah.
Sure. Thank you. Thank you very much. Thank you for the interesting presentation.
Thank you, Mr. Taji. I would like to request all the participants to turn on your camera so that we can take a screenshot of our participants for our publicity purposes. And if you have any more questions, please feel free to ask. And we will provide the email address of our speaker at the chat box. Please check the chat box. And I would like to request Martinus and Sabbir to take the photograph of our participants. So
please everyone, turn on your camera if you feel comfort. I'm taking the first page photo. Okay, next page. Okay, done. Thank you. Thank you, everyone.
Thank you, Martinus and Sabbir. Dear participants, please feel free to ask your questions to our speaker if you have any.
Yes, if you have any questions, feel free to ask me. I am here. Yeah.
So it was a very nice presentation. So thank you, Dr. Habib, for such knowledge sharing. So I have a question that is more little bit related to your topics. That is, you mostly focused on actually the hollow core fiber. There is and solid core fiber. The comparison and traditional fiber. There is another type of fiber that is porous core fiber. Yes.
Yes,
now,
you're right. Yeah.
Yes. Now, what is the future of those who are working with porous core fiber? Then, what they will do? Do you have any indication out there?
So I have to be very honest with you, right? So basically, this porous core fiber normally used in. So by the way, where are you from?
So this is IoT, Islamic University of Technology.
Okay. So when you ask any questions, I would prefer you, introduce yourself. It's better.
Oh, okay, okay.
So to be honest with you, actually, this kind of porous fiber normally used in terahertz.
Yes.
Okay. So it has been, long, couple of years that several papers has been out from porous core. I don't feel myself there is a future. I mean, there's a very little scope there now because lots of work has been done from this porous core, and there's a little applications of this kind of fibers. You can get it. I mean, if you switch from the porous core fiber to this kind of fiber, still you can use in terahertz.
Okay.
So we have some publications from this that we switch from porous core fiber, from Kagome structure or like hollow core intrusion fiber, so that you can do this. But personally, what I feel that there is not so much future. Even though if you go for like PhD, I would not recommend you to do research on porous core fibers. It's to be honest with you.
Okay, thank you. Thank you very much for your honest reply.
Dear participants, do any of you have any more questions to our speaker?
Well, if no one has any questions, Dr. Salim, I'm sorry to disturb you again. I would still like to ask you one more question to you, sir.
Sure, go ahead.
So you just mentioned, sir, like for PhD, what should we be focusing on? Or like when we select a topic or when you're looking into prospective supervisors or PhD, in which area should we focus on currently?
Can you please introduce yourself?
Okay, I'm Qazi Tariq. I'm currently working in a photonics lab in King Fahd University of King Fahd University of Minerals in Tehran, Saudi Arabia. So I work with, currently I'm working in millimeter wave generation with semiconductor lasers, which are quantum dash lasers or quantum dot lasers even, for the application purpose of communication. Okay.
So what's your question now?
My question is, since I'm looking forward to getting a PhD or joining some lab, I'm looking into a prospect is, for instance, since I'm working with semiconductor lasers, I see that the amount of power that we have is actually very limited. Also, it has to do with the beam width, and it's very difficult to work with such tiny lasers. And
yeah, you're right.
To the best of my understanding, currently, even though in the research field it has very good application, but not probably in the state of the market or in the state of the art in the future. So I'm looking towards something so that I can branch out and have some value in the near future.
So I'm guessing that you're more about lasers rather than the fiber, right?
Exactly. Okay, sir. Okay, now here is another question. So I have been suggested that I can look into fiber lasers rather than just lasers itself.
So truly speaking, actually, is a huge field if you come to like fiber laser, like high power fiber lasers. So in our group in Creole, so we have recently, we have a very powerful laser, to be honest. But the laser that normally used is it's not all fiber. So what we are doing now, we are trying to develop all fiber high power laser. What it means is that rather than the conventional fibers that are really bulky, right? You have a very big cavity.
Yes, big laser.
It's very big cavity, right? So what we do rather than doing this, so in our lab, especially, my supervisor, my ex-boss actually, because we can draw the fiber. This is the very good advantage that we do. We can draw fibers. This is the main advantage in my group. And the second advantage is that after drawing this fiber, we can make very special type of fiber. We call is like yttrium dope. Have you heard the name?
Yes.
Erbium or yttrium dope.
Erbium dope fiber.
Erbium dope fiber, or or yttrium dope fiber, whatever it is, depending on the pump wavelength. So we really have. We can get a very high peak power or high average power from this fiber.
May I know what is the power that you're talking about approximately?
Oh, still our target, to be honest with you, we are talking about kilowatt range of power.
Okay, yes.
Right, it's huge, but it will take time because now the world leading group is in IANA, in Germany. They do this kind of fiber lasers, but they are using. They have been using in this business for several years. But recently we started, but I think we get up to 1 kilowatt. I think 1 kilowatt or something like this. It's a very initial stage, but we can go to 100 kilowatt or something like this, but it's step by step. But I would suggest you to, if you come to United States, it's a huge opportunity that if you really focus on all fiber lasers, it's a huge market here.
I understand, yes.
Yes. and you can get easily job. I think in Apple, Google, they are now doing lots of fiber stuffs. Or
Okay,
you can go to geometric optics. Yeah.
What about, let's say, if I focus in, I currently was looking into DTU, from where you actually completed your PhD. So I know this is one of the best labs currently even working in most of the new researches. So what about if I talk about Europe or Canada?
I mean, if you go to DTU Photonic in my lab, it's awesome, I would say. You really learn a lot. And
yes.
I mean, it's very, competitive, to be honest with you, because
definitely,
I know, let's say, if there are 60 students apply in just one position, 60 students apply. I saw it when I was about to finish my PhD. So one of my friends, Christos Marcos, he showed to me, actually, look, Selim, that there are 60 students. It's very difficult to, get
select,
it. Select.
So
what
would make me maybe come at the top of the 5 participants in case if I'm applying for it? What skills or lab skills or any criteria that would be actually good for application?
I think if you already are familiar with fiber, right? If fiber lasers lasers.
Yes.
I think it's enough. I think you're already qualified.
What about in terms of publication?
Is
it necessary to have several publications, conference as well as?
No. They will actually. The thing is that how it works in Europe actually it's my opinion. It might change or vary, right? Personally, what I feel that they really prefer. I don't know why they prefer European students. I don't know why.
Yes.
I mean, I was so lucky to be there, and I was the first Bangladeshi actually in DTU Photonic. I was the first ever. Okay.
Yes.
But even definitely if you go to Germany, because in photonics industry, I would say that I think Europeans are still leading over USA.
So, okay, if not DTU, sir, what about the next lab that you would be suggesting?
If you can go to Max Planck.
Max Planck, yes.
It's very good. If you go there, it's very good. Max Planck Institute, you can go there, or you can go Jena in Germany.
Okay.
Thank you, Mr. Tariq Kazi, for your questions. Sir, we have got a question from Alma Fuz. Here, sir, I have a question. When we will design a HC-ARF fiber, what will be our main focus? Is it to reduce the loss?
Again, it depends on, it depends on the application, right? So if you are really focusing on designing this fiber for fiber optics communication, okay, then of course reduces the loss. But if you are focusing on nonlinear application, we don't care so much about the loss. Yes.
Okay, I think Alma received his answer. So we are already out of our time. So please, if you have any more questions, please feel free to contact our speaker to his email address. He has already provided his email address in our chat box. And with the permission of our speaker, we will publish this video in our Facebook, in our YouTube channel. So take care, and sir.
Okay, thank you very much. Again, thank you very much for your
in the session, and thank you again for your time. And we want to thank you again for participating in our webinar series from IEEE and Convetional Bangladesh.
Okay, thank you very much.
Thank you, sir.
Thank you, everyone.